Hello, my name is Eugen. I'm glad to be here at the Linux Plumbers. So thank you everyone for joining my talk today. So today I will explain a bit about my work in the past year. It's called Meminspect. Now it's called Meminspect. And the main goal of this talk is to show you a little bit about it and then to get some feedback from you, because that's the most interesting part for me, is to get your opinion on it, your feedback, and help me improve it and get it better as it goes. Because in the past year there have been several patch series, a lot of feedback. So what's the current state of the patches? It's thanks to everyone who reviewed and got involved in this. So I will just give you like a quick motivation and overview of what it is, what's the goal, what's the purpose, and then I will show you how exactly it's done now. So this is like a very quick, high-level overview of what it is, what's supposed to be do. So in that first blue big thing one, you have like the whole kernel memory, which is big, made of a lot of chunks. And the goal of this Meminspect is to pick out several things from that memory and recreate it in a smaller state that could be useful for someone. So if we want to inspect the kernel to find out several vital information from it, we don't need this whole memory. And also, we don't know where inside that memory the interesting things for us are. So what this Meminspect proposes is to get a way to annotate all this kind of memory into a table, that's the lower part of the photo, in which we can find out some vital information about the kernel, even if it's running, or it's dead, or it's frozen, or it's crashed, or whatever state the kernel is. So this is like a high overview of what Meminspect should try to do. So I put a photo there in case someone missed the first slide. So as I said, we want to analyze the kernel, but we do not need the whole memory. We can use the whole memory if we want, of course, but that's not feasible in all kinds of situations where you don't have access to all the memory, or maybe you cannot dump it, or you cannot have a way to read it or parse it, the whole one. So what can we do is to analyze this kernel with a much smaller memory footprint, so the table below. So why would this be useful, and why would we need that, and what would be the purpose of it? I have a previous talk at Linaro Connect, which is the full motivation. There was a Linux alignment on that. So there is a lot of background to check. But in short, the idea would be to get some memory and to be able to debug it, to use it, to inspect it, to analyze it, but without the whole memory. Of course, we have this drawback that we are not able to analyze the whole kernel. That's something we have to live with. But in some cases where the small little memory is very small, we can find out some debugging information that would be useful for someone in that case. So the idea would be to do that, to find out this small little table and to use existing tools like the crash tool that can be loaded, can load such a table of memory and then find out some useful information from that. So what is the proposal that I've been implementing and testing it? It would be to mark all those red little regions from the memory of the kernel and then add them to some table for specific purpose, like analyzing the kernel, debugging the kernel, and so on. So we don't need all those pages. All those pages maybe are some unuseful data, some drivers we don't care, some memory pages we don't care. We don't need all that to debug. So what we would need is like some vital pieces. I gave you some examples there, like number of IRQs, number of threads, how many CPUs are there in this system, GIFs, the architecture, for example, Linux banner or the UTS struct, print keyring buffer and things like that. So all these kind of things help us debug the kernel or analyze the kernel, find out what's going on in the kernel, but without actually having the whole kernel memory, like a usual dump. So how to do that, how to mark all those regions and add them to that table, having some specific goals in mind. One of the main goals is to avoid to interfere with existing code as much as possible. So how can we select all those pieces of memory, all those chunks, without interfering too much. I don't want to barge in subsystems, add code, add a lot of functions, be bloated, add bloat to the kernel, make it more complicated than it already is. So the goal would be to make it as simple as possible to avoid people saying, hey, I don't want this in my subsystem, I don't want this in my code, don't change this, it works like that. But somehow to make this work without interfering so much. And a second goal would be to make it simple. Not be so complicated with a huge API, something that would be very difficult to understand and difficult to use. So that being said, I have already 2 real use cases that make this work in a real product. And those are parts of the patch series and can be tested by anyone. So the first one would be the Qualcomm mini-dump, which is some kind of firmware-assisted dumping mechanism in which the firmware can read that red table, that one-line table below, and can select all those memory chunks and recreate a small little cute dump called mini-dump that can be loaded in some usual tool like Crash and then can be read. So with the help of the firmware, we can select all those memory regions and copy them and extract them from a kernel. And the second would be the Kane for Android debug. That's a driver that's on the Pixel phones, and they are using it to extract, again, vital information from the kernel, and they're copying some data into some reserved memory, and their bootloader just reads that and then parses it and gets some useful debugging information from it. So those are 2 use cases that could make use of that and make it work. So during the past year or even more behind that, there have been several proposals on how to do this, how to achieve such information. So I tried to reuse pstore, go through pstore, go through a backend of pstore. There is a link to the patches there. There was an RFC posted on that. I made 3 versions, RFC versions of something called kmemdump, is a previous iteration of all this. There are 3 versions there. There have been a lot of feedback on that, so thank you everyone who contributed there and gave ideas and so on. At some point, the idea was to rename it to Meminspect because it was too much of a dump in that kmemdump, to make it like a more generic way of marking memory regions for inspection. So the result is what I call now Meminspect. And the patches are there in the 6th link. That's the available patches. So that being said, like a quick introduction, let's see how Meminspect will basically select the data from the kernel. And the first thing that would be of interest is how to mark some static variables that are in the kernel that we want to be able to select in the inspection table. So this is what is done today. There is this cute little macro called Meminspect entry, which takes an ID, a symbol, and a size. And it creates a static structure in here, you can see, in a dedicated section called the inspection table. And in there, it stores information on this static variable. A specific ID, a specific address to a virtual address point, like a pointer, in fact, and the size. So it will annotate the variable into this table that's created at compilation time. It will be there in this table, and then it can be used by the Meminspection core, let's say, to create a bigger table out of it. And I've added another cute little macro, which is even simpler than that. Just takes the symbol, generates some ID from it, uses size off, and it's really simple to use in the code with the least interference possible in the code. And to show you how it's done, in this case, when you define your variable, let's say in this case number of IRQs, it will just have a cute little macro, 1 line, simple entry for this variable. And it will store its address, its size into the inspection table. So how does this look like? Anyone has any kind of opinion on it? Do you like it? Do you don't like it? You have someone there who wants to ask something.
If there's a lot of some of these small bits of kernel data, it seems like there's a lot of overhead to have a separate table entry for each. Has there been any thought to, say, putting a bunch of these in a separate linker section, where then you can say include that entire section in the Meminspect table.
Yeah, that's a separate linker section there. It's called section inspect table.
I mean, like putting number IRQs itself in a like .data.memin .data.critical or something that we then you would have one Meminspect entry that says, here's all the data that we want to include in the dump.
That would be one way, but it would mean that I would need to allocate this number IRQs like that in a separate section.
Right, yeah, with like an attribute, yeah.
Yeah, so it would add an attribute to number IRQs. So I don't know if that would be fine for everyone. I mean, if the IRQ maintainer Thomas would like to have an attribute on number IRQs to be stored in a different section compared to everything else in IRQs. Or all the other variables, GFIs and everything else would be stored in a different section. So if that is okay for people who maintain all these variables, then I'm fine with that. But this was a way to just make it work at some point. But again, what you say is viable. It could be done. Move all the critical variables in a separate section. But it has to be like wanted by everyone. Yeah?
Just a question, but it also means that everybody or every subsystem has to annotate every variable.
You don't have to do anything. If you want your variable to be like marked for inspection, being in the inspection table, then yes, you can annotate it. If you don't care about the inspection table or you don't want your variable to be in there, you can simply ignore it and you don't need to add anything. This is like completely optional.
Yeah, but when you want it to be included in the dump or in the data, then you have
If you want to be included, you can just annotate like this, everything. You have your own dedicated driver and you want to annotate a static variable, you do this. And then your inspection table will contain it, an entry corresponding to it. So that's doable and it's optional and it's your choice. You're not obliged to do anything related to that.
Can this be solved with BPF?
I don't know.
I have to make the joke, but
I don't know.
But the reason I say that is that I find it like when I'm debugging things, usually the subsystem maintainers don't necessarily care about me, not in a negative sense, but they don't want to have to think about the fact that I'm going to debug them. They want to think about the feature they're working on, and they don't want to maintain and add new entries and convert. You know what I mean? They don't want to have to think about debugging. So so like, is there a possibility where you could have this done more dynamically?
Yeah, this is for static variables. I will show you how to do it for like
all right.
kmalloc things or dynamic variables or memblocks. So I have like 3 different things to do that. Yeah?
Yeah, I think the concern that's being raised here is that the people who might care about doing debugging might be, for example, a company's data center kernel team, and their desire to want to do debugging and what they want to debug may be different from what the kernel maintainer cares about. And so therefore, it might be interesting if there was a way to easily express that some set of variables should be in this inspectable region without having to make, a whole bunch of out-of-tree kernel patches, right? So for example, if we could have a list of variables, it's like, please put all these variables in the inspection, and it's, you don't actually have to modify the .c file, it's just something that the linker or part of the build process would take advantage of. That might be an interesting elaboration of this particular technique. I don't think it needs to be there for the initial, 1.0 minimal viable product, but I predict that when, the data center kernel teams want to start using it, and they go back and try to get, a whole bunch of patches into all different parts of the kernel, that might be an interesting discussion that would take place, and then we might need to come up with some other solution.
Some people are quite reluctant to what they call linker magic. So they kind of say, I want to have control in my C file and not really not know what the linker magic is doing. So, David, you want to?
So I agree that sounds interesting, but like my understanding so far was that usually you would use kdump in an environment and you would get everything you need. But what we are focusing on here is primarily like these devices where you only have like specific, like small areas of you can only store like a certain number of areas where you can actually dump something. And most of the cases that you identified here that you add, for example, number IQs is actually to get kdump even like do like the, no, not kdump, but the crash tool actually do something reasonable, right?
Yes.
So it's like all like what you focused on is like the minimal number of variables that you need to even get like crash to even identify something.
Yeah,
right?
and I will show you how Crash will load the image with like 50 or so minimum number of things that Crash really requires. Because when Crash loads the dump created with this table, from this table, it will try to look how many CPUs are there, what's the root section of memory, and so on. If something is not available, it will crash and say your dump file is broken.
Like regarding the point about data centers, do you see a use for data centers with that, or is like a data center they just use ordinary kdump and like they have
Some people use ordinary kdump and that's fine for them, and they have enough storage to keep ordinary kdump. But
well, yeah. So I think if you have, I can imagine situations where if you have a very, very large number of machines, you're running at massive scale, like you're a hyperscaler, and if some of your customers are really, really paranoid about not having any kind of PII or customer cryptographic information leak into the kdump, this might be a way that you can actually get kdumps when you might not be allowed to otherwise, right? So I could imagine use cases where that would matter.
I'll just quickly add that.
Sorry, sure.
And that's exactly the another use case we have. We just presented 1 hour back for the trusted VMs, where we use this framework or version of it. And I'm from Qualcomm. We are using this from last 12 years for mobile. And we do this for encryption of memory, because with this trusted VM dumps, we do not want some of this information to be leaked up. At the same time, we want very small memory. You can have 2 MB or 3 MB of that dump just for RMA purposes. On the device, you can just dump it over eMMC, and then send it to Qualcomm, and we can just look at it. That's enough information for us to start analysis.
Thank
you. Okay.
I mean, just to your point, like I think traditionally you would use like make dump file, and make dump file just throws out all of the user pages, and you could throw out other stuff. But I think then like Meminspect would come in handy, that you could say, well, actually, like I need like these areas, and I don't care about like hardware limitations, but it's actually like used in a different context. So that makes sense. I think we roughly discussed something like that, to exposing that to user space somehow as well, these areas, or including it in the what is it called, the VM
Core Info.
VM Core Info, exactly.
Yeah, one of the patch series, the V3, uses all the implementation moved to VM Core Info and having a lot of things there, but it's also a bit tricky with static variables and dynamically allocated memory, which is not named. Let's say you kmalloc into an array with a pointer, and then you save it somewhere. It would be difficult to parse or to find. So coming back to one of the questions that was asked about dynamic memory and so on. So this is like what I did in the latest patch on dynamic memory, because we had this discussion on whether we should put wrappers, which I personally disliked. David also disliked the wrappers on the mem block. So I was trying to be as least invasive as possible to add like a cute little flag, let's say, where we could not modify the API itself for memblock. That would be the same, and people using it would have to say the same, no change. But it would add like this API that's already is in the memblock with mark something and clear something. So there are some few APIs there already that select flags like from that list. You can mark scratch, clear scratch, or whatever. So I added these two little APIs to mark a memblock for inspection and clear it from inspection. And that flag is there. And then in your code, you just need to call this function, mark inspect, when you do a memblock alloc. So this would be like a minimal interaction with memblock. Because some of the things that crash tool wants when it loads a crash dump is to have access to all these kind of mem sections, to read them and recreate the table inside the crash memory. So those are needed by crash tool. And of course, maybe someone else wants memblocks. For me personally, not really, but crash tool wants those. So how is this API looks like if you just need to call this mark inspect at some point when you're allocating. And then when you free the thing, you can clear inspect, or that could be done automatically if the memblock is removed or unallocked. But most of these memblock allocations are never freed, like sections or something. They are allocated at early boot time, and some of them never freed, like ring buffer, for example. It's allocated and never freed during the lifetime of a kernel. So we don't really much care about clearing the inspect flag unless maybe someone wants to reallocate the buffer at some point. But even if so, and if we don't clear the inspect, it will be just another section in the table that would be more or less useless. So how does this look for you, David? Do you have any opinion on that? One thing else, we could put this flag inside this memblock alloc or panic. But it was a bit difficult because all these flags are masked inside memblock API. This goes to some other API, and then it uses an API to get flag, and it looks up the flag corresponding to somewhere the memory was allocated and so on. So it's not a flag that's passed directly from the user like this memblock alloc.
Yeah, so I think the question of whether or not it is acceptable to have a couple of extra memories dumped really depends on the requirements of why it is that we're trying to do this. If this is, for example, a way to be able to get debugging information out of a confidential compute VM, for example, then we absolutely would want to make sure that when you free memory, that it gets taken off of the dumpable list. If it's just to try to minimize the size of the kdump because it's a consumer-grade device, and if you leak a little bit of information, not a big deal, you don't care. So I think it really depends on the assumption of why it is that you're trying to do this thing.
The answer would be to cover cases for as many use cases as possible. Yeah. So if the confidential computing feels like this should not be there, it can be removed. So if it's something that it's usable by someone. So I want to make something like a more generic API that can be used by multiple use cases. So someone using this feature would have to be extra careful if they want to do like confidential something. Or if they don't care, then they simply don't care. But the API and the implementation should cover like helping everyone. That's what my take would be on that. I don't want to focus on a specific use case because that would make it very niche or very specific to someone and would not be usable by anyone else, you know?
Yeah, so we had the same question in the morning when we presented trusted VM one, then the confidential compute. So I just talked to Anish a few minutes back. On the RMM side for the ARM CCA, right? So we have not reached to that stage. The problems is similar to what you are explaining, but adding the design of RMM and the CCA for the ARM, we have not reached to the use case of this, but we need to solve the same problem there, including the encrypting the memory when you are doing a dump. So we can do another backend, is what we just talked for 5 minutes to maybe when it comes for this development of Meminspect with the over RMM. So, yeah.
So when the users of this table come into hand and they want to use it, then they can selectively pick areas from that red line and then create their own whatever they want to do. So the Meminspection API would be usable by anyone who wants to tap into this table, and I will show you exactly how consumers can tap into that. So that's one other thing to discuss after we discuss a bit on how to select the memory, and then I will have a slide on how to use the selected memory.
Just one more thought. I mean, we briefly heard that like it would be nice if you could just pass in like a number of like names and then like magically you get the right things. Did we explore how we could use debug info to at least like for all of the variables derive like what would be there? Because at least like for the static stuff that like the debug info contains like where is which variable, how is it called?
When you
like,
load
does it
the
reside?
dump with crash tool just reads the symbols from VM Linux, which contains all the debug information, like structure sizes, offsets, names, and everything for all the members. And then crash tool batches what's in the debug symbols with the actual data from the dump. So you can see all the members and the structures and stuff with the debug info from VM Linux, and then match it with the actual core. You cannot use crash with only this dump because you don't have access to the actual information, structures, members, and so on.
Yeah, I believe, David, you thought about excluding variables by passing the debug info. Is that correct? Because that's at least something mekdump file can do. So you can filter out certain memory regions from the dump by parsing dwarf info.
No, that's not what I mean. What's rather thinking like we annotate like all of the variables right now in the kernel which we want to have like part of this table, and I was just wondering like if this could be more dynamic, that like if we have the information in the debug kernel somehow in the kernel itself like composed, that you could just say, well, like this file like tracing or whatever, like this file and this variable, please like include it in the next like in the not included in the dump, but include it, for example, in stuff that I want to have in my static areas. Right? Mekdump file is like a later stage. Like I'm talking about, like you're running on the kernel, you want to include something in these areas or whatever. So you would just like instead of like annotating all of the variables, you would instead like somehow be able to derive that from debug information.
Yeah, or annotate the whole file, static section. Or something.
I don't know like how, but I'm just wondering like the debug info, we have all of this information, and if we could compose that into something that the kernel could just load, and you as a user could say, well, like instead of saying like number IAQs or whatever, I can say, well, like this file like number IAQs, and it can just map it, well, that is located here in memory because like the kernel got loaded, whatever, it can just like derive that. Then you wouldn't have to annotate at least all of the static variables that we have somewhere.
Let's explore that. Yeah.
Are you talking about generating like a list of addresses that you would then like say parse the debug info from vmlinux.o, generate this, and then embed it in VM Linux? Or are you saying like have a like a debugfs or something that you could at runtime load a the first okay.
So those are the memblock cases. So I have also some other use cases that some random subsystem or driver want to register some memory into this inspection table. So I created all these function calls. So right now this is not at compile time, this is for like dynamic memory. And again, it's something that the user should just pass an ID, a pointer, or a physical address in this case, or a size and a type for this memory. And this will be added to the table at runtime. And I will give you an example here. The kernel config data, for example, that's stored in some assembly section. It is there. It adds in the assembly section some markers, and then the kernel config data. So to just add that to the table, it would be useful to use this API with a virtual address, like a pointer to the kernel config data, with a specific ID and with a size. So in this case, I'm making here a small little computation on where exactly is the config data in the memory. So this will be exactly added to the inspection table with a pointer to that address with that size, so it can be then selected and for analysis. So there are all these variants of combinations with an ID with a physical address, or just physical address and the ID doesn't matter, or with an ID and a virtual address, or just a virtual address, in which case all the IDs are derived from that. So this would be for like a dynamic address. Any opinions on that? Does this work? Is it fine to do it like that, or you have maybe some better ideas on how to just select some data that's in the memory? We have a pointer to it. It's not a static variable. We don't need to annotate the pointer itself, the kernel config data, but rather the memory which it points to.
I'm just curious, like we talked about, like when you say dynamic memory, is it all about memblock allocation, or are you also talking about like?
Memblock is done in that part because there are some things allocated with a memblock, but not part of the kernel allocator or some part of other sections or stuff like that. And that memblock things, like mem section and stuff like that, number of section roots and so on, like for example, the kernel ring buffer is allocated using memblock. Some other things are, we have a pointer to it. There are in a specific section, like the kernel config. It's written after you build the kernel, there is a Qtl script that takes the config and places it into the section. And then you have some assembly code in the kernel that gets your pointer to that config data, to that actual.
So like what I'm wondering is like as soon as we're dealing with other like virtual addresses, right? Like memblock is mostly like virtual to physical, like you are contiguous. As soon as we deal with virtual address space, you might no longer have physical continuity.
Yeah.
And I think at that point you would have an issue with, but I don't know, you have 2 pages in your
Yes.
virtual address space, and it's actually like 2 different physical ones.
Different physical,
So you could not possibly include that like in one of the sections here. I'm just trying to like wrap my head around like how you would handle
the
that.
table would hold a pointer to the virtual address and the size. So anyone trying to use that, if it's larger than 1 page, then obviously there is something that has to handle that when passing the table. If it's big enough, you have to probably register multiple regions, depending on what you want to do with that inspection table. What the consumer wants to do when parsing that table and finds out this section, this entry is too big to be contiguous. So that would be like the freedom of the driver or the consumer that wants to parse the table. So at the moment, I left it for the consumer to handle that.
So if you're doing some sort of like post-mortem memory dump, then you might require the memory dumper to do page table walks then to do that lookup?
Either at the memory dump or maybe at the driver level. For example, I will give you an example for the Qualcomm mini dump. The Qualcomm mini dump, it will look into the firmware will look into that address, and the driver itself will walk the table and find out the address. It will convert to a physical address, and then if the size is too big, it will have to create some multiple entries or whatever it's doing specific to that firmware needs. So it can be that the firmware could walk the table, or it can be that the driver would walk the table at the moment it registers the memory with the firmware. So that can be done ahead of the firmware actually interacting with the memory itself. It can be post-processing after Meminspect comes to play. The driver could post-process it however it sees fits. So that's one way of doing it. So that's this option, and let me show you how consumer drivers will interact with the table. So as I said, there are 2 ways to interact right now. So one way is to traverse the table. So I just created like a callback function for each entry that will get a cookie and an entry. And then the consumer driver will just call traverse with this callback. And the Meminspect code will go through the table, the inspection table, and call the callback for each entry. So what you were asking is what happens with the driver. The driver will just traverse the table, it will get an entry with a virtual address and a size, and then it will figure out, do I need to register this into, I don't know, my reserve memory? Do I need to copy it? Do I need to save it? Do I need to pass this to firmware? How am I passing this to firmware? Am I passing it like a physical address? Am I passing it as a virtual address? Is it too big to be passed as a single entry? Maybe I need to split it, things like that. So right now, I let the driver calling traverse to handle that. So the inspection table should be, from my opinion, as simple as possible. Just call this callback for the driver, and the driver wants to, ignore it maybe. He doesn't care about that specific entry, or he needs to parse it, or needs to do something else. One idea was to have like entries with different classes, so different consumers would be interested in a specific type of entries. And another way to get interacting with the table would be to get all these notifiers. So I created this like simple wrapper on the notifier. So I'm a driver that handles the firmware. I want to know when someone wants to register some memory in this inspection table. So when someone calls register into Meminspect table, the Meminspect code will just look to see how many drivers have been registered to be notified, and I notify them all. And again, there will be a callback called saying that, here you go, you have a new entry, or some entry was deleted from the table. So you can adjust if you want something was removed or something was added after you traverse. So the use case would be traverse at probe, get your table ready, look into what's done before your driver probed, and then register a notifier if you're interested in some new data that would be coming up at a later point. And that's how the notifier call does. So unlike previous versions which I had for kmemdump, where there was a specific backend that could be connected and removed and so on, with this system, you can have a whole bunch of drivers that would be just connecting to the table whenever they want. And you're not limited to just one driver accessing the table. You have anyone using this API can access that table and can traverse it and be notified and so on. So I know if this is better or not. There is pros and cons, I guess. So your take on this? Anyone has any opinion on how to access the table itself?
So you're maintaining a table and you're also having a notifier that can get called back, right?
Yeah.
So
I guess so.
I'm just wondering, like, it seems to me like only one is necessary, unless you, in the sense that if I would like to have a table of all the useful memory regions, then I write a driver that holds that all in one array or something like that, right? Which is what this table that you would traverse does. So I could just be I could just get notified, right?
Yeah.
And then if I guess I'm maybe I'm overthinking this, but it seems I like the idea of the callback, that then you can report it to firmware or something, but then is the memory used for this table not really important or being wasted if the firmware callback is just talking to firmware each time? It doesn't need a table in memory, right?
The table just holds addresses and sizes. So it's quite small and not really memory impactful. So it does not copy entries into the table. It's just holding addresses to regions.
Sure,
So
yeah.
the firmware is just like a pointer and a size usually, and the type. So it's like a pre-allocated table of 1,000 entries or whatever defined macro you have there of, I don't know, few hundred kilobytes. So that's a few hundred bytes, like 1 or 2K, 4K, something like that. So that's the whole table size.
Mm-hmm. I mean, fair enough. I'm just saying, yeah, I was just saying that.
If it were to copy regions, that would be a different thing.
Yes.
Having just like a metadata for the regions, in fact, the table is like a metadata for the regions.
Yeah.
Okay. So that's the API. I have here some additional info. Just this additional info
Maybe
is...
question for you and others as well. Like, what's remaining to get this accepted? So from last 6 months, we kind of made it more than Qualcomm. Of course, some of the comments also we resolved and kind of made it better. So what else you are looking for to get it accepted, or you see that some of these issues are open? So you know any blockers to get it accepted, or you want to share?
Right now, it is. There should be more people reviewing it and get more opinions on it.
So definitely, I want to openly say here, right? And maybe I'll mention it on a mailing list too. Qualcomm will use it. Qualcomm will convert this driver and use it in mobile, auto, IoT, XR, VR, or whatever you call it, Linux or Android-based products. So we are going to use it. So if you get it accepted. Of course, we have our version of it, but we want to move it to upstream version, which is better for us. So just if you want some
Yeah, so
assurance
all
openly.
this Minidump works in downstream and on the products that Qualcomm is selling. So they are using it in a downstream way.
Yeah, but
this
we will
would be a
switch to
way
this one.
that would be upstream and usable by multiple people. So one of the
Well,
goals
Auto already needs the upstream version, by the way, just because of the safety reasons and other stuff and compliance and everything. So the Auto, we will switch to that. And of course, we'll switch it everywhere. So just in case if anyone wants to know, like, hey, what is the use case? Is anybody going to use it? Once you upstream it, so it's not using downstream, I hope they're not going to continue using the fork, etc. Right? So,
yeah.
sorry.
So here I had some cute little slides on how when
So,
Flash loaded is to
to upstream use case, if you haven't already participated, you could go, say, talk about how you're using it to any of the patches
Yeah.
that are on upstream. Oh, I mean, right. You have to go review and say, hey, yeah, right.
Yeah, so this is how it looks when you load the dump. It reads a lot of information, like usual crash tool. So it finds out all this kind of information from the dump, from the table that's created by the firmware. You can read the log buffer and so on. You can print GFIS. You can print number IRQs, as I said. And of course, when there is some region of memory that's not available in the table, in the Minidump, in a small table, it will just say that it cannot read. So that's expected. That's what the goal is, to have a small little memory footprint dump and be able to analyze some of it, of course, not with the whole kernel, but with some of it into it. And as Trilog said, I'm eager to know, I thank you for everyone for all the feedback, and if you have ideas, if you have things that look like a red flag, say, no, this is a blocker, I'm totally against it, or something like that, please come and tell me, and I can think of something to find a way to accommodate everyone's needs, because this, I know, will touch some various aspects of the kernel. So, and also, if you think that this is fine and you're happy, then let me know on the mailing list here to see how could this go into the upstream kernel. Which way would be the best way to do that, how to get there. So that, because that's the goal, and to have people in production really using this, because the user is there, people are there. It's just a matter of getting it done in a way that helps everyone. It doesn't upset anyone, it doesn't bother anyone, it doesn't barge into things that it shouldn't, and it would be something that will be helpful. So yeah. Any other last questions or comments or something on the chat? There is nothing there. So, oh, one question there. The ball.
We're out of time, but
Yeah, last question.
Yeah, less a question, more a comment. So at least for the kdump use and for us as a big distribution, I don't think it's very useful in this way, because we have to support a lot of different hardware and different combinations and everything. So figuring out what piece in the driver is important, etc., is very difficult on this, big and very diverse environments. But where I could see a use in what Ted also mentioned is maybe if we could also have a mode that negates this table. So instead of saying, please include this data, please exclude this data, because it's maybe some sensitive data, it's some, big I/O buffers we don't care about in the dump, just to, give make-dump file a hint and make it easier for make-dump file to say, okay,
Everything
I don't have
is
to
excluded by default. So if we want to block something from being included or something like that, yeah?
Yeah, but that basically says, okay, I need a huge table with everything included, except maybe those small parts. And then you had a mode like that says, okay, we include everything from the kernel except for those buffers or those keyrings or whatever.
I get it.
Sensitive, then it would be a lot easier for us.
Could think of something of that. Another use case I could give you is with pstore. Pstore could tap into the table at panic time and collect data, store it into RAM oops, MTD oops or whatever, and make it available after reboot. So that might be useful for someone who does not have the firmware or the hardware or something that's involved. So there could be an implementation of a pstore, let's say, driver that would tap into the table and store it in a penny handler. So I didn't have the time yet to do that, but it was an idea that came up, and I think it's pretty neat to be able to read in pstore some binary data or some information that was in the previous run, except the message or whatever pstore is doing right now, today. We're out of time? Yeah, thank you very much. If someone has any other things to discuss,
You can continue the conversation outside, and yeah, you
have
can
a
continue
nice
that.
lunch and see you.
And there is a raised hand, but we're out of time at the moment.
Sorry. Feel free to contact me, and if you have a raised hand, just ping me or find me somewhere. Email me. Thanks. Bye.
Thank you very much.